Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to imagine, just for a moment, that you are tasked with assembling like a grand, sweeping family tree.
Okay, sounds fun.
Right. But this isn't human ancestry. You're mapping out a cosmic family tree, tracing the lineage of the most extreme gravity-warping objects in the universe.
Oh, black holes.
Exactly, black holes. And as you lay out all this data, you hit a wall. You realize something profoundly weird. An entire generation is completely missing.
Yeah, a massive blank space.
Right. Like, we can easily see the colossal ancient ancestor sitting at the top of the chart, and we can clearly identify the tiny, numerous descendants scattered all over the bottom. But the middle generation is just invisible.
It's completely absent.
A glaring blank space. You probably heard of supermassive black holes, those absolute monsters lurking at the center of galaxies. And you almost certainly know about the smaller ones, the stellar mass black holes formed from dying stars. But today, we're venturing out into the utter void of deep space to find the missing middle.
We really are. And it's one of the most frustrating yet mathematically tantalizing blind spots in modern astrophysics.
Tantalizing is a good word for it, because we're going to look at how researchers are taking one of the universe's greatest mysteries.
Fast radio bursts.
Yeah, these fleeting, unexplained flashes of radio waves from deep space. And they're essentially repurposing them as cosmic flashlights to expose those elusive middleweight black holes.
It's wild because the fact that we have the extremes perfectly documented, but the bridge between them has eluded us for decades, it suggests that, well, either our theories of how the universe grows are fundamentally flawed, or these objects are hiding in a way we simply hadn't anticipated.
Right. And before we talk about how we're finally hunting them down, let's establish why it's so strange that we can't find them. Let's talk about these cosmic weight classes.
Good idea, because size dictates completely different physics here.
Exactly. So at the very top of the hierarchy, the undisputed heavyweights, we have supermassive black holes. These are the anchors, right?
Yeah, the anchors, like Sagittarius A star at the center of our Milky Way.
Right. And virtually every other major galaxy has one.
Yeah.
And we are talking about masses that are millions or, even billions of times the mass of our sun.
To give you a sense of scale, the black hole at the center of the galaxy M87, which was famously imaged a few years ago.
Oh, the glowing donut picture.
Yeah, the glowing orange ring. That one is about 6.5 billion times the mass of our sun.
Billion, with a B.
With a B. These supermassive objects are the gravitational pivots for entire galaxies. And, their origins are actually still heavily debated.
Really? Like how they got so big?
Yeah, whether they started out as smaller seeds that merged over billions of years, or if they collapsed directly from massive clouds of gas in the early universe. But regardless of how they got there, they are loud.
Right. They aren't exactly hiding.
Not at all. They're surrounded by accretion disks of superheated plasma that shine brighter than the rest of the galaxy combined, so we have no problem finding them.
They're the cosmic lighthouses.
Exactly.
And then, at the other end of the observable spectrum, we have the lightweights, the stellar mass black holes, the descendants, if we're keeping with the family tree analogy.
Right.
These are born when a massive star reaches the end of its life, runs out of nuclear fuel, and the core just collapses under its own staggering gravity.
Yeah, and these usually weigh in at roughly 5 to a few tens of times the mass of our sun.
And the physics of stellar collapse,
Yeah.
it puts a natural cap on how big these can get, right?
It does. When a star is massive enough, the pressure and temperature inside its core gets so incredibly high that it actually triggers this phenomenon called pair instability.
Pair instability, what is that?
It's where photons, literally particles of light, spontaneously turn into electron-positron pairs.
Wait, light just turns into matter?
Yeah, under those extreme conditions. And when that happens, it causes a sudden drop in outward pressure. The star collapses, and the resulting supernova completely obliterates the star. Leaving absolutely nothing behind, no black hole at all. Because of these mechanisms, standard stellar evolution really struggles to produce black holes much heavier than, say, 60 to 100 solar masses.
Okay, so we've got the supermassives and the stellar ones. But just to put all our cards on the table, there's also a theoretical featherweight class, right?
Yeah.
Primordial black holes.
Yes, primordial black holes. And these are distinct because they weren't born from dying stars.
They predate stars.
Entirely. The theory goes that in the chaotic, high-energy environment, just fractions of a second after the Big Bang, the universe wasn't perfectly smooth.
It was clumpy.
Right. There were microscopic quantum fluctuations. In some incredibly tiny regions, the density of matter and radiation was so intensely concentrated that it just collapsed directly into black holes.
Before atoms even existed.
Exactly. And depending on exactly when they formed in that first split second, they could theoretically be the mass of like an asteroid or a mountain, but squeezed down into a space smaller than a single atom.
Okay, so we have the supermassive giants anchoring galaxies, the stellar mass remnants scattered around, and potentially these tiny primordial specks left over from the dawn of time.
Right.
But then we look for the intermediate class, the middleweights, the intermediate mass black holes.
The missing link.
Theoretically, these should weigh somewhere between 100 and 100,000 solar masses.
Yeah.
But we look out into the universe and, well, nothing.
Nothing conclusive, yeah.
It's like exploring the African savanna. Right.
Mm-hmm.
And you find millions of mice, and you find massive herds of elephants. But you look around and realize there is absolutely zero evidence of anything the size of a dog or a gazelle or a horse.
That's a great analogy.
Are we just bad at looking? Or are the laws of physics actively preventing them from forming?
Well, that is exactly the debate that has raged for years. From a theoretical standpoint, they absolutely must exist.
Why must they?
Because the supermassive black holes we see in the early universe are too big to have grown from stellar mass black holes purely by eating surrounding gas.
The math doesn't work out.
Right. There simply hasn't been enough time since the Big Bang for them to get that heavy. They had to have merged from intermediate seeds.
Okay, so they have to be out there. Why can't we see them?
Finding them isolated today is notoriously difficult because unlike supermassive black holes that have entire galaxies of gas and stars swirling around them, an isolated middleweight black hole wandering through space doesn't have a glowing accretion disk.
So if it isn't eating, it isn't shining.
Exactly. If it isn't actively feeding on something, it emits no light. It is a completely dark object against a completely dark background.
But it's not just about filling in a blank on a spreadsheet, is it? It's not just, oh, we need to collect the middle one to finish the set. Why do astrophysicists actually care so much about finding an object in this specific weight class?
Because they represent a pristine environment to test what physicists call strong field gravity.
Strong field gravity. Break that down for me. You mean areas where gravity isn't just pulling a planet in an orbit, but doing something fundamentally more aggressive?
Yeah, exactly. Think about the gravity we experience in our solar system.
Okay.
It's incredibly weak. Even the gravity of the sun, which keeps Earth in orbit, is considered weak field in the context of general relativity.
Really?
Yeah.
The sun is weak.
Cosmologically speaking, yes. Newtonian physics can describe almost all of it perfectly. But near the event horizon of a black hole, space-time is severely, violently warped.
It gets weird.
Very weird. It is stretched and twisted in ways that push Einstein's equations to their absolute limits. Testing our theories of physics in these extreme environments is crucial.
But couldn't we just test that on the supermassive black holes?
We try, but they are incredibly messy environments. They're filled with magnetic fields, plasma jets, swirling matter, radiation.
It's too noisy.
Exactly. An isolated intermediate mass black hole would be a clean, quiet laboratory. A pure distortion in space-time without all the astrophysical noise.
That makes a lot of sense. But the history of trying to find these things is just a string of heartbreaks. I mean, every time we think we have one, it slips away. Let's talk about the Omega Centauri controversy.
Oh, yeah. The classic cautionary tale in this field.
Because I think that perfectly illustrates how maddening this search has been. So, for context, if you aren't familiar with Omega Centauri, it is the largest globular cluster in the Milky Way galaxy.
It's huge.
It's this incredibly dense spherical collection of millions of ancient stars, all packed tightly together, orbiting the center of our galaxy. And back in 2008, it made massive headlines because it seemed like the missing link had finally been found right in our cosmic backyard.
I remember that.
Observations from the Hubble Space Telescope and the Gemini Observatory down in Chile suggested that there was a massive invisible object sitting perfectly in the center of that star cluster.
Yeah, the researchers were looking at the kinematics of the cluster, specifically how fast the stars right at the dense core were moving.
Like bees swarming a hive.
Right. By using the Doppler shift of the light from those stars, they measured the velocity dispersion, and they found that the stars near the center were whipping around much faster than they should be, based on the visible mass of the stars alone.
So there was extra gravity coming from somewhere.
Exactly. The gravitational math seemed inescapable. There had to be a central concentrated mass of about 40,000 times the mass of the sun pulling on them.
40,000. So right in that intermediate sweet spot.
Yep. And since it emitted no light, it perfectly fit the profile of an intermediate mass black hole.
I remember when that paper came out. It felt like a slam dunk. We found the missing link, but then the scientific method showed up to ruin the party.
Well, ruin or refine, depending on how you look at it.
Right enough.
The problem with looking into the center of a globular cluster is that it is a dynamically complex, chaotic environment. Follow-up research heavily disputed those 2008 claims.
How so? Did they get the telescope data wrong?
No, the data was right. Other teams just build incredibly complex N-body simulations, computer models that calculate the gravitational interactions of millions of individual stars over billions of years.
Wait, so they didn't just disagree with the data, they disagreed with what the data meant.
Exactly. The counter-argument proposed a mechanism called mass segregation.
Mass segregation.
Over billions of years, the heavier objects in a star cluster will naturally sink to the center due to gravitational friction, while lighter stars get pushed outward.
Like heavy rock sinking to the bottom of a river.
Yes. So what if that dark mass at the center wasn't one single 40,000 solar mass black hole? What if it was a swarm of a few thousand stellar mass black holes, neutron stars, and dead white dwarfs that had all sunk to the core?
Oh, wow.
They would be invisible, they would collectively have enough mass to make the other stars whip around quickly, and they wouldn't require us to invent a new class of black hole to explain them.
So the definitive proof basically just evaporated.
Pretty much.
Could be one giant thing, or it could be a swarm of small things, and from Earth, it just looks the same.
Right.
As it stands now, despite decades of staring into the hearts of these dense star clusters, the existence of intermediate mass black holes remains entirely unconfirmed. We are 0 for 0.
Which forces a paradigm shift. If you can't find the invisible object by looking at the stars swirling around it because the environment is just too crowded and noisy, you have to find a completely different method.
You have to look at what the black hole does to light that just happens to be passing by it from somewhere else.
Exactly.
And to do that, you need a very specific kind of light, a very specific probe, which introduces the second massive mystery of our conversation, fast radio bursts.
Oh, yeah, FRBs.
Now, if you are not an astrophysics nerd, you might be thinking, okay, a radio burst, what's the big deal? But fast radio bursts, or FRBs, are the tools that astrophysicists are now trying to use to find the missing black holes. And they are wild.
They really are.
To understand how this works, we need to talk about what an FRB actually is. Or rather, what we observe them to be, since we don't actually know what they are.
They are arguably the most active mystery in astronomy today. I mean, the first one was discovered purely by accident in 2007.
Wait, by accident?
Yeah, it was retroactively found in archival data from the Parkes Radio Telescope in Australia. It's often called the Lorimer burst, named after the astronomer who found it.
And when we say fast, we really mean it, don't we?
Oh, absolutely. These are transient pulses of radio emission. An FRB can last for as little as a tiny fraction of a microsecond, maybe up to a few seconds on the extreme long end.
But most are over in the blink of an eye.
But it's not just their brevity that makes them astounding. It's what that brevity implies about their power.
Right. Because they're coming from far away.
We know these bursts are coming from outside our galaxy, and we know this because of a property called dispersion.
Dispersion. Okay, how does that work?
As radio waves travel through the incredibly sparse cold plasma in the intergalactic medium, the lower frequencies get slowed down just a tiny, tiny bit more than the higher frequencies.
Like light passing through a prism.
Very similar, yeah. So when the burst hits our telescopes, the high frequencies arrive a fraction of a second before the low frequencies. It smears out. By measuring that smear, that dispersion measure, we can calculate roughly how much space the burst traveled through.
And the dispersion measures for FRBs are huge.
Massive. They tell us these flashes are traveling across billions of light years of space. Now just think about the energy required for that.
Oh, man.
For a signal that lasts a fraction of a millisecond to be detectable by our telescopes here on Earth, after radiating outward in all directions and crossing billions of light years, I mean, the source of that burst must be unimaginably powerful.
How powerful are we talking?
We are talking about an event that releases as much energy in 1 millisecond as our sun emits in 3 days.
In 1 millisecond?
Yeah.
Okay, I have to stop and push back on the logic of this entire endeavor right here. Let me get this straight. We are trying to solve the mystery of the missing intermediate black holes.
Yes.
To do this, we're using another completely unsolved mystery, these fast radio bursts, as our primary tool.
We are.
That feels like trying to find a hidden object in a pitch-black room by using a flashlight, but you don't even know how the flashlight works, who manufactured it, or who is holding it. From a rigorous scientific standpoint, how is that sound? How can you use an unknown to measure an unknown?
It sounds like a paradox, I know, but it's actually a deeply established tradition in physics.
Really?
Yeah, sometimes the behavior of the probe is actually more important than its origin. If we return to your darkroom analogy, it genuinely does not matter if you don't know the brand of the flashlight or what kind of batteries it uses or the chemical composition of the bulb.
Okay.
What matters is that it is projecting a powerful, incredibly sharp, clean beam of light straight across the room.
Because whatever that beam of light hits or passes through is going to alter the beam. And we can measure the alteration even if we don't know the source.
Precisely. Even if we don't know if an FRB is created by a highly magnetized neutron star, a colliding binary system, or something completely beyond our current physics, we know its properties as it travels.
We know it's a straight line of radio waves.
Right. We know it acts almost exactly like a point source of light. We know it emits a sharp, coherent burst of radio waves crossing vast cosmic distances. That makes it a perfect, naturally occurring backlight for whatever it bumps into along its journey to Earth.
It's an ideal tool for eliminating the invisible obstacles in the deep universe.
Exactly.
Okay, so let's put the two pieces together. What exactly happens when this mysterious microsecond flash of radio waves bumps into an invisible middleweight black hole? It isn't like shining a flashlight at a brick wall where the light just stops or reflects, right? Gravity does something far stranger. It creates a very specific kind of cosmic optical illusion. And this brings us to the core mechanism of the whole search, gravitational microlensing.
This is where that severe warping of space-time we mentioned earlier comes into play.
Right, the strong field gravity.
Yes. Gravitational microlensing is a direct, observable consequence of Einstein's theory of general relativity. Mass bends space. John Archibald Wheeler famously summarized it. Space-time tells matter how to move. Matter tells space-time how to curve.
I love that quote.
It's perfect. But the thing is, space-time also tells light how to move.
Let me try to visualize this. Let's say a galaxy 3 billion light years away fires off a fast radio burst. That little package of radio waves starts traveling in a perfectly straight line toward Earth.
That's right.
But directly in its path, lurking completely unseen in the darkness of intergalactic space, is an intermediate mass black hole. As that FRB gets close to the black hole, it doesn't just fly straight past it, right?
Yeah.
Because the space around the black hole isn't flat.
Exactly. The black hole is acting as what we call a point mass lens. Its extreme gravity has created a deep depression, a severe geometric curve in the very fabric of space-time around it.
Like a bowling ball on a trampoline?
Yes, the classic analogy. It's not that the light is being pulled by gravity the way a planet is. Rather, the light is always traveling in a straight line, but the space itself is curved.
So the straight line becomes a curve.
Right. So when the FRB enters that warped region, the path of the light is forced to follow the curve of space bending around the black hole.
Okay, let's say I'm looking at a candle on a table, and I place, not a funhouse mirror that just scatters things. What if I place a thick, curved piece of glass right in front of the candle, like the base of a thick wine goblet?
Okay, yeah.
The curved glass physically bends the light rays from the candle. So when the light finally reaches my eye, my brain, which assumes light travels in straight lines, traces those bent rays backwards and sees two distinct candle flames instead of one.
That's spot on.
In our cosmic scenario, the black hole is the base of the wine glass, bending the radio burst.
That is a phenomenal way to picture it. The gravity of the black hole forces the light to take two separate paths around it to reach us. But here is what's crucial for the researchers. How does this bending actually look to our telescopes when we analyze the data?
Because we can't actually see two flashes of light, right?
No, we don't have telescopes with the spatial resolution to actually see two separate flashes of light in the sky. The angular separation is incredibly tiny on the scale of milliarc seconds or less.
Right, because an FRB is so far away, it's just a single pixel of data hitting our radio dish. So how do we know it was split?
Time. The speed of light is absolute. If an FRB travels through empty space, our telescopes record a single sharp spike of radio waves, a single peak on the graph.
Okay.
But if that FRB has been microlensed by a black hole, it took two different paths to get here. And in the geometry of curved space, those two paths are almost certainly not the exact same length.
So one path is longer than the other.
Exactly. Furthermore, the light traveling closer to the black hole experiences a deeper gravitational well, causing what's known as the Shapiro time delay.
The Shapiro time delay, what's that?
It means time itself moves slightly slower in a stronger gravitational field relative to the observer.
Oh, wow. So you have the physical path being longer and the local time for the light ray literally slowing down.
Yes, exactly. So one path takes a tiny fraction of a millisecond longer to reach Earth than the other path. The single burst of radio waves arrives at our telescopes at two slightly different times.
Like an echo.
It appears on our readouts as a clear multi-peak structure. One burst superimposed with its own echo, arriving mere milliseconds apart.
Wait, if I'm tracking the physics here, this isn't just a neat visual trick. This is essentially a scale, isn't it? A mathematical scale to weigh the invisible object.
It is exactly a scale. The time delay between those two peaks, that split-second difference in their arrival, is directly mathematically determined by the mass of the object that bent the light.
Really? Just from the delay?
Yep. The heavier the black hole, the deeper the space-time curve, the wider the paths diverge, and the longer the delay between the original pulse and the echo.
That is wild.
By measuring that tiny delay between the echoes, physicists can work backward through the equations of general relativity and calculate the exact mass of the invisible lens.
That is breathtaking. Which means, if we find the right kind of echo hidden in the data of a fast radio burst, we can precisely weigh an invisible black hole that is billions of light years away and completely dark.
That is the theory, yes. And it is an elegant application of physics. But until recently, it was just a theory.
Why?
We simply didn't have enough high-resolution data on fast radio bursts to search for these microsecond echoes.
And this is where the groundbreaking new research comes in. This is where theory hits reality. A team led by Huan Zhu at the School of Physics and Optoelectronic Engineering at Yangtze University recently put this exact method to the test.
They did.
They didn't just write another theoretical paper, they went hunting. They dove into a massive database called the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. Specifically, the CHIME FRB Catalog 2.
Right.
Now, I want to talk about CHIME for a second because it is not what you picture when you think of a telescope.
No, not at all. If you picture a giant steerable satellite dish pointing at the sky, you have the completely wrong image.
Like the one in Contact.
Yeah, exactly, the Arecibo kind of dish. CHIME isn't like that. It looks more like a series of 4 massive snowboarding half-pipes sitting out in a valley in British Columbia.
Snowboarding half-pipes.
It consists of 4 cylindrical parabolic reflectors, each 100 meters long, with no moving parts whatsoever.
It just stares straight up.
Right. It relies on the rotation of the Earth to sweep the sky. But what makes it so revolutionary is its digital backend. It uses an incredibly powerful supercomputer correlator to process massive amounts of radio data in real time.
This is more computer than telescope.
In many ways, yes. It essentially forms thousands of digital beams to monitor a huge swath of the sky simultaneously. Because FRBs can appear anywhere at any time without warning, you need a telescope with a massive field of view.
You can't just point a small telescope and hope one happens.
Exactly. CHIME is essentially the ultimate wide-angle lens for transient radio signals. It has completely transformed the field, building a comprehensive catalog of hundreds of these fleeting bursts.
It is a treasure trove of data for researchers looking for anomalies. So Huan Zhu's team analyzed this vast catalog, searching specifically for FRBs that exhibited that clear multi-peak structure, the telltale echo of gravitational microlensing.
And they were incredibly thorough.
Right, they meticulously ruled out bursts where the multi-peak structure could be caused by noise in the data or known scattering effects from interstellar gas. And out of all the data, they found 2 very specific microlensing signatures that stood out.
And this is where the rigorous mathematical modeling pays off. When they applied those general relativity lensing equations to the precise time delays of those specific echoes, the numbers they got were extraordinary.
The moment of truth. They calculated the mass of the invisible lenses that caused those two echoes. For the first signature, the mathematics inferred a mass somewhere between 539 and 609 times the mass of our sun.
Incredible.
And for the second signature, the inferred mass was between 1,544 and 2,571 solar masses.
Both of those specific ranges, around 600 solar masses and around 2,000 solar masses, they sit perfectly, squarely within that elusive intermediate mass black hole gap.
They fit right in the blank space on the family tree.
Yes, they are far too heavy to be stellar mass black holes and far too light to be supermassive black holes.
Okay, but let's play devil's advocate here. Let's say I'm an astrophysicist reading this paper, and I want to be as skeptical as possible.
Please do.
We found something heavy that bends light. We know it weighs, say, 2,000 times the mass of the sun. But how do we know it's a black hole? Space is full of stuff. How do we know the light wasn't bent by a really dense, dark cloud of gas, or maybe a really tight, ancient cluster of dead stars, like what they thought was happening in Omega Centauri?
It's the essential question, and the answer lies in the specific constraints of the point mass lens geometry. To bend light in this very clean, specific way, to create that distinct, sharp, unscattered, multi-peak structure from a coherent radio burst.
The echo.
The echo, right. The mass doing the bending must be unimaginably compact. The physical size of the lens has to be smaller than the Einstein ring radius it creates.
The Einstein ring radius, meaning the physical spread of the bent light.
Exactly. If the object doing the bending is physically wider than the paths the light takes around it, the light just hits the object or passes through the object and gets scattered, absorbed, or smeared out. It doesn't create a clean echo.
So a gas cloud wouldn't work.
Not even close. A cloud of gas weighing 2,000 solar masses would be diffuse. It would be spread out over light years. It wouldn't bend the light sharply like the base of a wine glass.
It'd just be fog.
Exactly. The radio burst would pass through it, and the free electrons in the gas would smear the signal entirely, changing its dispersion measure in ways we could easily identify.
And what about a tight cluster of dead stars?
Even if you packed thousands of white dwarfs and neutron stars together as tightly as physically possible without them merging, a cluster of 2,000 solar masses would still be far too physically large. Plus, an environment that dense would be incredibly violent.
Lots of collisions.
Stars would collide, accrete matter, and emit their own ambient light, X-rays, or thermal radiation. We would detect that surrounding noise.
But the data shows nothing.
Nothing at all. These lenses are completely dark, and their gravitational focus is razor sharp. At these specific mass ranges, physics dictates that an object this massive, this physically compact, and this completely electromagnetically silent can really only be one thing.
A black hole.
The matter has to be crushed down below its own Schwarzschild radius. It has to be a black hole.
That is staggering. Finding these specific masses, actually weighing these objects and seeing they fit the missing middle way profile is a monumental achievement on its own. It feels like we finally have our first real, tangible map to the missing generation we talked about at the beginning.
It's a huge milestone.
But here is where the research takes a massive turn. The researchers realized that where these objects are located might actually be an even bigger discovery than their mass. The spatial context of these two detections might literally rewrite our understanding of the early universe.
Yes, the location factor here shifts the paper from a great astrophysics discovery into profound cosmological territory. Because when the team analyzed the line of sight, meaning they calculated the direct path from the origin galaxy of the fast radio burst through the invisible lens all the way to the CHIME telescope on Earth, they realized something profoundly strange about the environment surrounding these black holes.
Right. Usually, black holes are anchored in galaxies, or at least dense star clusters. They're born in stellar nurseries, they live in galactic disks, they are surrounded by matter.
Yeah, they have neighbors.
But in the case of these two specific microlensing signatures, there are no intervening structures. There are no galaxies, no galaxy clusters, no vast webs of visible matter along the line of sight in the immediate vicinity of the lens.
Which leads to a startling, almost eerie conclusion. These black holes appear to be completely isolated. They are drifting completely alone in the vast, empty, intergalactic voids of deep space.
So if you're trying to figure out why this matters, think about the origin story. If an intermediate mass black hole isn't inside a galaxy and there is no evidence it was ever part of a star cluster, how did it get there?
It challenges the standard models fundamentally. If it's isolated in a void, it couldn't have been born from a dying star because stars don't form in intergalactic voids. They need dense clouds of gas to ignite.
Right, they need a nursery.
And it couldn't have formed from a runaway collision of stars in a dense cluster because there is no cluster. The environment necessary for that kind of stellar evolution simply isn't there, and it's highly improbable that a 2,000 solar mass black hole was somehow ejected from a galaxy without taking any stars with it or leaving a massive gravitational wake we could detect.
Which brings us right back to the theoretical featherweights we mentioned at the very beginning of the show, but scaled up. Primordial black holes.
Exactly. This is why the researchers explicitly suggest these candidates are strongly pointing toward a primordial origin.
Because they formed before anything else.
Right. Because primordial black holes formed just a fraction of a second after the Big Bang, long before the first atoms even combined, let alone before the first stars or galaxies formed. Because they predate galaxies, they wouldn't necessarily be bound inside them.
You just drift.
As the universe expanded, these primordial black holes would simply be carried along, scattered throughout the cosmos, drifting in the intergalactic voids.
Okay, if we are seriously entertaining the idea that these are primordial black holes floating in deep space, we have to talk about the elephant in the room. We have to talk about the dark matter connection.
Oh, yeah.
The big one.
Because this is where this research scales up from, hey, we found a missing black hole, to we might be potentially solving one of the biggest, most enduring mysteries in all of physics.
It is the ultimate cosmological crossover episode. I mean, for decades, since the pioneering work of astronomers like Vera Rubin and Fritz Zwicky, scientists have known that the visible matter in the universe, the stars, the gas clouds, the planets, us, it only accounts for a tiny fraction of the actual mass out there.
15%, right.
Roughly, yeah.
Yeah.
When we look at how galaxies rotate, the stars and the outer edges are moving way too fast. Based on the amount of visible matter we can see, those galaxies should literally fling themselves apart. The gravity of the glowing stuff isn't strong enough to hold them together. But they don't fly apart. They hold together, which means there has to be an immense amount of invisible mass providing extra gravity. We call it dark matter, but let's be honest, that's just a placeholder name for the invisible stuff creating the extra gravity that we don't understand.
Precisely. It's a label for our ignorance. And the particle physics community has spent decades looking for new, exotic, subatomic particles to explain it. Things called WIMPs, weakly interacting massive particles.
Right.
But despite billions of dollars and incredibly sensitive underground detectors, we haven't found a single one, which has led many astrophysicists to revive an older theory. What if dark matter isn't a microscopic new particle? What if it's macroscopic?
What if the universe is simply teeming with an unseen population of primordial black holes?
Exactly. Because they would exert massive gravitational influence, they emit absolutely zero light, and they don't interact with regular matter unless it falls right into them.
They perfectly fit the job description of dark matter.
They do. So Huanzu's team took their two candidate black holes, looked at the volume of space CHIME surveyed to find them, and calculated the statistical implications. They ask, if these two microlensing events are indeed real primordial black holes, what does that imply for the dark matter population as a whole?
And the math they came out with is fascinating. They extrapolated from their detections and determined that if these are true primordial black holes, then black holes specifically in these intermediate mass ranges, the 500 to 600 and 1500 to 2500 solar mass brackets, could account for approximately 4% of all the dark matter in the universe.
Now, 4% might sound like a small slice of the pie to someone outside the field. But in the context of dark matter, where we have spent decades with exactly 0% of it definitively identified.
Literally zero.
Yes, zero. So finding an entire specific category of objects that can count for 4% is a revolutionary leap. It provides a massive, tangible constraint on cosmological models.
If you're wondering why finding 4% of something is a big deal, think about it this way. You have a massive jigsaw puzzle with missing pieces. For years, you didn't even know what color the missing pieces were. Now, someone has just found a handful of pieces and proved they are blue. It doesn't finish the puzzle, but it completely changes how you look for the rest of them.
It is a profound constraint. It begins to chip away at the absolute unknown. But what's equally impressive, and what makes this a truly rigorous piece of science, is how they handled the alternative scenario. The statistical analysis in the paper doesn't just rely on hoping their interpretation is right.
Yes. What fascinates me about this paper is that this is a win-win for science. The scientific method is working flawlessly here. Because even if these detections turn out to be false alarms, even if we later prove that these specific echoes weren't caused by black holes at all, the math still works backward to give us an answer.
It really does.
It's like playing a massive cosmic game of guess who. Even when you ask, does the suspect have glasses? And the universe says no. That no is incredibly valuable because it helps you eliminate a huge swath of suspects on the board.
Exactly. This is the failure scenario. And in Bayesian statistics, a null result is just as mathematically valuable as a positive detection.
A null result.
Right. The authors calculated that if these candidates are not true gravitational lensing signals, if there are actually 0 intermediate mass black holes acting as lenses in the entire CHIME dataset, we still learn something vital about the composition of the universe.
Because we looked so hard and found nothing.
Right. By not finding them in a survey this large and sensitive, scientists can establish with 95% confidence that primordial black holes heavier than 300 solar masses cannot make up more than 13% of dark matter.
So either we have found the missing middleweight black holes and simultaneously identified 4% of dark matter, or we have definitively proven that heavy primordial black holes are not the primary ingredient of dark matter, capping their entire contribution at a maximum of 13%.
Either way, the boundaries of the unknown shrink. The error bars get smaller. We are closing in on the truth.
It is a structural win for astrophysics. The constraints narrow, the theoretical models get refined, and the parameters for the next generation of radio telescopes become infinitely more precise.
Absolutely.
But, and there is always a but in astrophysics, before we officially declare the mystery of the missing middle solved, before we rewrite the textbooks on dark matter and primordial cosmology, there is one massive caveat hanging over this entire study.
The caveat.
And this caveat is exactly the kind of complex, nagging variable that forces scientists to be incredibly cautious.
Is the great scientific what if, and it brings us right back to our lack of fundamental understanding regarding the fast radio bursts themselves.
We established earlier that we are using a mysterious flashlight to find a hidden object. We know the light is hitting our telescopes as a multi-peak structure, an echo. We've shown how beautifully the math aligns if that echo is caused by an intermediate mass black hole bending the light. But the alternative explanation for those multiple peaks challenges the very foundation of the microlensing theory.
Right. We have to confront the intrinsic emission mechanisms of the fast radio bursts. Because we do not know what physical, astrophysical process creates an FRB, we cannot say with absolute certainty how that process operates dynamically from millisecond to millisecond.
Wait, let me make sure I'm following. You're telling me the multi-peak structure, the echo that perfectly aligns with the general relativity math of a 2,000 solar mass black hole, might just be the flashlight flickering twice on its own, rather than a single continuous light being bent into two by gravity.
That is exactly the degenerate caveat. It is entirely physically plausible that the source of the FRB itself stutters.
It stutters.
Yeah. Let's say the burst is caused by a magnetar, a highly magnetized, rapidly rotating neutron star undergoing a massive starquake that snaps its magnetic field lines.
A starquake? That sounds intense.
It is incredibly intense. If that cataclysmic event pulses rapidly, emitting two distinct bursts separated by a fraction of a millisecond, those two pulses would travel across the universe and arrive at our telescopes looking completely identically indistinguishable from a single burst that was split into an echo by gravitational lensing.
Oh, that is brutal.
It would perfectly mimic the geometric signature of a black hole.
It's a cosmic counterfeit. The intrinsic stutter of the source perfectly imitates the gravitational lens. So how do we break that tie? If the time delay looks exactly the same on the graph, how do we prove we are seeing a true spatial echo caused by gravity and not just an intrinsic flicker from an unstable magnetar?
That is the frontier we are on right now, and it requires us to look at properties of the light beyond just when it arrives. It requires an extraordinary level of rigorous skepticism, which the authors of the paper explicitly acknowledge. To definitively prove these signatures are intermediate mass black holes, we need to analyze the polarization of the radio waves.
Polarization. Okay, break down how that helps us tell a stutter from a lens.
Think of polarization as the orientation of the light wave as it travels. Does it wiggle up and down or left and right?
Okay, I can picture that like shaking a rope.
Exactly like shaking a rope. When a magnetic field generates a radio burst, it gives that burst a very specific polarization angle. If a magnetar stutters and emits two bursts, the massive magnetic field of the star is likely shifting, rotating, or violently reorganizing between those two pulses.
Because it's having a starquake.
Right. Therefore, the second pulse will likely have a slightly different polarization angle than the first pulse. The microscopic physics of the source change over time.
I see where you're going with this. But what if it's a gravitational lens?
If it's a gravitational lens, there is only one single burst of light. The source is identical. The gravity of the black hole splits that single burst into two paths, but gravity is achromatic.
Achromatic.
It affects all frequencies and polarizations exactly equally. It doesn't twist the orientation of the light differently on the left path versus the right path. So if we look at the two peaks of the echo and their polarization angles are identical down to the finest measurable degree, that strongly implies a single source was lensed.
Wow.
If the polarizations are different, it's almost certainly an intrinsic stutter from the source.
That is an incredibly elegant solution. So why didn't they just check the polarization in this CHIME data?
Because capturing that level of granular polarization data for transient microsecond events is incredibly technically demanding.
It's just too fast.
Yeah. The CHIME data provides the time delay beautifully, but we need more comprehensive, multi-layered observational data from next-generation arrays to routinely capture the exact frequency distribution and subtle polarization wave interference patterns across the peaks to distinguish a true gravitational echo from a source that just happens to be flashing twice.
It's like we've been handed an ancient treasure map to the hidden monsters of the universe. We can see the X marking the spot, the coordinates line up perfectly, but we're still trying to learn the specific dialect of the legend in the corner. We aren't quite sure if we're reading the topography correctly yet.
That's a perfect summary of where the science currently stands. The CHIME catalog has provided us with our most incredible, mathematically robust candidates to date. The math of strong field gravity holds up flawlessly if these are indeed lenses.
The puzzle pieces fit.
They do. The profound implications for primordial black holes floating in voids and their contribution to dark matter are revolutionary. But the final, definitive proof, the thing that will lock this into the textbooks, requires us to crack the code of the fast radio bursts themselves.
It is an incredible journey. Just to recap how far we've come, we started with a massive missing generation in the cosmic family tree, the intermediate mass black holes that the laws of physics demand must exist, but observation has entirely failed to confirm.
Right.
To find them, we had to stop staring into the noisy, chaotic centers of dense star clusters and instead repurposed mysterious microsecond flashes of extreme radio waves from deep space as our cosmic flashlights.
Exactly.
By analyzing how the extreme gravity of hidden mass bends that light to create split-second echoes, scientists have essentially found a way to mathematically weigh completely invisible objects billions of light years away. And in doing so, they are simultaneously closing in on the secrets of dark matter and the chaotic quantum moments just fractions of a second after the Big Bang.
It truly showcases the incredible ingenuity and resilience of modern astrophysics. When that direct, obvious approach fails, you don't give up. You use the warping fabric of space-time itself as your instrument.
It really does. And I want to leave you with one final, lingering thought to ponder tonight as you look up at the night sky. We are so entirely used to looking at the stars, the bright, spiraling galaxies, the visible, glowing structure of the universe. We assume that the light is where the action is.
It's natural to think that.
But if this research holds true, if these middleweight black holes are indeed primordial, isolated, and making up significant chunks of the dark matter that silently binds the cosmos together, then the vast, seemingly empty black voids of deep space between those glowing galaxies aren't empty at all.
Far from it.
They are silently teeming with invisible ancient behemoths, middleweight monsters born at the very dawn of time, completely undetectable to us, drifting alone in the absolute dark, until they briefly, fleetingly cast their shadow in the light of a microsecond radio flash we still don't even fully understand.